Edexcel Core Pure, second order differential equations 2, non-homogeneous case. Particular integrals, the special cases. We've already seen that first we solve the homogeneous case in order to get the complementary function, and then we look at the non-homogeneous case in order to find the particular integral. And together these will satisfy the general solution. It's worth just stressing that the complementary function will only satisfy the homogeneous equation which equals 0. That will be extremely important in a few moments. So some of the cases, non-homogeneous cases we've seen already. If it's a linear non-homogeneous case, we try a linear function. If it's a polynomial, we try a polynomial function. If it's any combination of trigonometric functions, we try both trigonometric functions together. And if it's an exponential function, then we try an exponential function in order to look for a particular integral. However, a problem can occur if we try to use a function for our particular integral which has already been used in our complementary function. To overcome this problem with a function, we simply take the particular integral we'd normally use and multiply it by the independent variable x. And this is similar to what we did when we looked at repeated roots to the auxiliary equation in an earlier video. And this will enable us to solve the differential equation and find the particular integral. So here, first we look at the homogeneous case and produce the auxiliary equation which we've solved for m, and that gives us a complementary function. And the really important thing about that complementary function is if we use the complementary function and substitute it back into the differential equation, it will only equate to 0 because that was the homogeneous case. We now have to look for a particular integral which will satisfy the non-homogeneous equation. So now looking at the non-homogeneous equation, which is 3e to the 2x, and bear in mind our solution to the homogeneous equation, we would normally try something like y equals a e to the 2x. And we would differentiate it once, and we would differentiate it twice, and we would substitute everything into the non-homogeneous equation. But e to the 2x has already been used in our complementary function. So if we try using it again, it will only allow us to equate the differential equation to 0 again because it came from the homogeneous case. So in order to fix this problem, we need to change the trial function which we're going to use, and we do that by simply taking a e to the 2x and multiplying by another x. So we've just seen that y equals a e to the 2x will not work. So instead we're going to try y equals a x e to the 2x. So we've multiplied by that extra x. So now we can find dy by dx with a product rule, and we get a e to the 2x plus a x e to the 2x. And the tiny little detail here is if you take out a common factor of e to the 2x, it will just make the second derivative easier to find. So that will give us d2y by dx squared is equal to differentiate the bracket, leave the exponential, plus leave the bracket, differentiate the exponential with a chain rule. If you just simplify this second derivative before we use it, we get a slightly neater form. So now if we substitute y and its derivatives into the non-homogeneous case, we will get a second derivative, as we can see at the top, minus a first derivative, minus twice y, and that has to equate exactly to 3e to the 2x. So the thing to note here is that normally for the non-homogeneous case we would try e to the 2x, but because it's already part of the complementary function, it will only solve the homogeneous case, and therefore we have to times by another x in order to get it to work. Finding the derivatives of y and equating it to the non-homogeneous right hand side will allow us now to find the value of little a. So if we collect like terms together, we will get 3a e to the 2x is 3e to the 2x, and therefore a is 1, and therefore we found a particular integral which will satisfy the non-homogeneous case, and it's y equals 1x e to the 2x. So by using this special case of the particular integral, we've been able to find the derivatives of y, equate it to 3e to the 2x, and that allows us to find a and the particular integral. So the complementary function, remember, only satisfies the homogeneous equation, which equals 0. This modified particular integral will now satisfy the non-homogeneous case, and together they give us a general solution. It still contains two constants a and b. And we can now look at the behaviour of these constants a and b and the solution by looking at a GeoGebra file. So there's some interesting features to note here. If we look for the y-intercept, so that's when x is 0, the y-intercept should be a plus b, so at the moment it is 2, and when a is 1 and b is 4, the y-intercept is 5. So the y-intercept will always be a plus b. So if we now look at what happens as x tends to infinity, the e to the minus x term will tend to 0, and we will have two dominant terms. So as x tends to infinity, we can see that the red solution isn't quite tending towards either of the two exponential curves, because both of them are dominant. One of them's positive and one of them's negative in some cases as well. If we look at x tending to minus infinity, so when x tends to minus infinity, the e to the 2x term and the e to the 2x term will tend to 0, and it's the b e to the minus x term that becomes dominant. So if we look at x is negative now, we can see that the red solution stays very, very close to the green exponential representing 2e to the minus x. And that brings us to the end of second order differential equations 2, the non-homogeneous case.